So the second is the APIs. As I told you, these APIs are very useful. APIs for communicating with operating system. So to run and stop programs and communicate with operating system, APIs are needed. APIs serve as the major way for user to interact with the operating system. APIs are interfaces that allow users to communicate their desire to the operating system. Thus, interfaces are essential for executing various operations on the system. So, operating system is an interface between the user and the hardware. So, the user uses APIs to communicate with the operating system. So, operating system as a resource manager, running multiple programs at once raises new questions about the operating system. A policy is used to determine which program should run at the given time, because the processor chooses. We will come in the future, the scheduler. We have short-term scheduler, we have long-term scheduler, and middle. So these schedulers, they use policies. We have a lot of policies so the operating system to choose which program to run next, okay? Policies are used in different places with the operating system to make decisions. Basic mechanisms implemented by operating systems, such as running multiple programs, require policies. Operating system serves as the resource manager by efficiently managing and allocating resources to different programs based on their need. So we will see in the scheduling, when we come to schedulers, we will see. Policies and mechanisms are the two important points in operating system. Whenever we think about operating system, policy and mechanisms are basic points. An operating system must implement various mechanisms and policies to efficiently manage and allocate resources as a resource manager. Mechanism also, for example, mechanism always, how can we enable concurrent execution of multiple programs when we have only one processor available? So these kind of questions will be answered by mechanisms. And the policy is which part, for example, which program should run now, okay? So these kind of questions will be answered by the policies part. So the timer, so policies, example, which program should run first, which should run next. Like we have a lot of scheduler, first come, first serve, FJs, round robin, etc. So we will see it in the minute. The next, what we are going to see is virtualizing the memory. Now we have seen with the course how to virtualize the CPU, the processor. So now we are going to see how we are going to virtualize the memory. Memory concept before virtualizing memory. What is memory? So let's get into it. What is memory and how does it work? Memory refers to a computer's ability to store and retrieve data. Primary memory or RAM is used for temporary storage, while secondary memory, hard drive or flash drive, is used for long-term storage. Binary codes 1 and 0s is used to represent information in the memory. And the CPU sends a request to memory to retrieve data. So these are the most important thing, because every program, before it runs, all its cores and all its data should be stored in RAM before the CPU starts processing it. What is a byte and a bit? As we know, a byte is a unit of digital information consisting of 8 bits. So a bit is the smallest unit of a digital information, representing 1, 0. So why are there 1024 bytes in 1 kilobytes? This is also, it seems a simple question, but because computer use a basic 2-number system, so 1 kilobyte is equal to the power of 10 bytes, that is 10, this 1024. byte. So when we think of byte, always, for example, when we say my computer is 64 gigabyte, that means 64 and how many zeros? 9 zeros byte, okay? That is what it means, okay? To the power of 9 bytes will follow. So computer 1 megabyte of memory consists of 1 megabyte will be to the power of 20 bytes. Each byte has an address resulting in to the power of 20 addresses in 1 megabyte of byte. So this is very important because our memory will have each byte, okay, will have its own address in the memory. So this is the idea. Memory is an array of bytes that store data. To read a memory, specify an address to access data stored there. So to access or to read, we have to know the address. To write or update memory, specifically data to be written to the given address. Programs access memory consistently to store and retrieve data structures. Various instructions like load and store are used to access memory. Each instruction of the program accesses memory while doing its work. It's important to note that each instruction of the program is also stored in the memory, so memory is accessed on each instruction fetch. So instruction code that manipulate data structure are also in the main memory. Don't forget this, okay? So as you can see, general memory size summary. To the power for 1 kilobyte, it has this byte. So 1 megabyte, it will have these bytes, and 1 gigabyte is like this. So our, for example, 64 gigabyte is like this, 32 gigabyte is like this. So this byte minus 1 will be the last memory address location, and because the memory will start from 0. So to get the memory address, just subtract 1 from the total number of bytes because the memory address starts from 0. For more information, please refer ASCII tables and the link will be here, okay? You can go and check this video. Now, virtualizing memory, we have a code from our textbook. So this is a program mem.c. This is also stored, I will show you in a minute, in our Linux system. So as you can see, we have the main part here, integer. We have RC character. This is a pointer, integer pointer, and malloc. This we have memory allocation of the size, and this A1 will allocate some memory to a pointer variable integer. So as you can see, allocate memory in line A1. Then print out the memory address. A2, if you can here, print address of P. As you can see, get PID, get the PID of the program identification PID, okay? Just what it does, print out the memory address in that location. Then if you come to 3, what it does is put 0 into the first slot of the memory. So as you can see the pointer, we have the pointer, so it will put 0 in that location. Then it will print the new. You see, once it gets the spine, it will spine and it will add 1 every time, okay? It will add 1 in that location, then get the PID and store that data into the location. So what it does is print out the PID of the running program with every print statement. To allocate memory, use a system call mallocate. To print out the memory address, use this. And to initialize the memory, use assignment this, as you can see, the pointer. To loop and increment, use a while loop, as you can see, while, and increment using pointer, arithmetic, and assignments. So to print out the PID, use a system code like getPID. So this is simple code, and let's go and see in our Linux system what it does. So this will be the how virtualization of memory works. We shall see in a moment. So what we are going to do, okay, so let's go here. Let's enter to our in the textbook. This is what happens. You see P1, P2, P3, P4, and the address of P was found like this in our. So the newly allocated memory is at address this as per the book. It updates the value and print out the result. Every second it adds 1 to it and prints that is what it does, okay? So we use a command below to disable, this one is very important for you. We use the command below to disable address space layout randomization in Linux, but for me it works. For you, if it doesn't work, just use this echo and enable address space randomization, and this one disable the randomization, okay, address space randomization. So when the program was executed, so the memory, okay, when we run it 2 times, okay, the memory was found in the same location, It is as if each program running has its own private memory, okay. Each running program has allocated memory at the same address. As you can see, each program was allocated in the same address as per the book. But for us, we will see it now. Each seems to be updating the value at this independently, because they are the operating system, it already virtualizes. That's why that's why it's doing like that. But let me go. What we are going to do? Okay, let me go here. As you can see, we have the memc file here. So what we are going to do, so let me minimize this one just for you to see. Okay, so what we are going to do, the same thing we are going to do, gcc and mem.elf and mem.c. okay, then what we are going to do, mem.elf. Let's invoke it, mem.elf. Now what I'm going to do, I will give only one. Let's see. So as you can see, Control C to stop it. So we put at this memory address, we give 1. Okay, this was integer, it was assigned in that pointer. Then every second it will increment by 1. Okay, that was the idea, and this is the address. Okay, this is the address for that process. This was the address. Now what I want to show you is the second step here. Let's go and see this one. What we are going to do now is mem.elf 1, and let's give another process now. Mem, again I am assigning again what I am doing is I am assigning a pointer. Okay, I am assigning a pointer the same location. Okay, .elf, let's say let's make it 200 now in this time. Okay, let's make it 200. As you can see, the two processes are running. What happened? This is magic. What happened? The same memory location, you see, the same there. What it does, they are running at the same time and it's updating, as you can see. Look, 2, 3, 4, 5. It's updating in the same memory location. This one also I started with 200. Every minute it should increase. So 201, 202, 203. You see? So the process one also updating in the same memory location. So this is the magic. Okay? This is the magic. So this is what happened. And let's go to our slide, and let's go to our slide. So as you can see, the virtual memory and the process isolation. Each running program has its own private virtual address space, which is mapped by the operating system on the physical memory. In the example, each program allocates memory at the same address, as you can see, but updates the value independently, as if it has its own private memory address. Okay? So a memory reference within one process does not affect the address space of other process or the operating system itself. Physical memory is a shared resource managed by the operating system using mechanisms like paging and swapping. Process isolation ensures that each process runs in an isolated environment, enhancing security and preventing interface. Virtual memory and process isolation are fundamental concepts in operating system covered in detail in this book. So as you can see, we see from the examples that each running program has allocated memory at the same address, and yet each seems to be updating the value at the same independently. Okay, independently. So this is the idea of virtualization of memory, because this cannot be because one address should not be shared by a lot of programs. I hope you understand the concept of virtualizing memory. Okay, so each process accesses its own private virtual address. Each process has its own private virtual address space. Virtual address space is mapped on a physical memory by the operating system, and memory references within one program does not affect other process address space, benefit improved security, isolation, and simple program development. Memory management unit translates virtual address to physical address, and physical memory is a shared resource managed by the operating system. Operating system ensures each process has access to the required physical memory. Operating system can move page of memory between physical memory and the disk.